One rather important process that we will be studying throughout the course is the isentropic process, and this is a process whereby there is no entropy change of the system. So for an isentropic process, what we're looking at is a system that is internally reversible and it is adiabatic. So that means that there is no heat transfer. It is an idealization, however, it is one that we will use throughout the course as kind of like the best case scenario for different types of processes. Another thing about entropy is just like we were looking with internal energy as well as enthalpy. For entropy, what we do is we set the value of entropy to be 0 at 0 Kelvin. So that becomes our base or reference state. So if the entropy at absolute 0 is 0, we will be using that when we're calculating the entropy at different points, just like we did in an earlier example where we're looking at both internal energy as well as enthalpy, being able to evaluate it at some reference point. Another thing, entropy itself is a quantification of the disorderly or randomness of our system. And what it is doing is it is quantifying the transfer of different forms of energy into random forms of energy, such as vibrational kinetic energy of molecules, for example. And so that is the thing that entropy is quantifying. So it's quantifying the transfer of energy into a disorganized form. And disorganized form of energy would be translational, kinetic energy at the molecular scale. So those are some of the different features of entropy. What we're going to do now is take a look at a number of different examples of entropy generation. The first one is one that you can actually test on your own, and that is mechanical friction. Whenever we have mechanical friction in the systems that we're studying, what is happening is work is being converted into random thermal energy within the system. And the easiest example of that is if you take your hands and rub them together, you're doing work and you can feel your hands getting warmer and warmer. That is due to the random motion of the molecules within your hands due to the friction. So that's one form of entropy generation. Another one we looked at when we talked about the weight behind a baseball. And essentially what we were saying is the drag force on a baseball is represented in the random motion in the fluid within the wake. The source of the drag is caused by either form drag or viscous friction on the baseball, and that in turn causes the fluid in the wake of the baseball to move around, and that becomes a random form of energy. And we talked about viscous dissipation. Viscous dissipation is the process whereby shear, so velocity shear, velocity differentials within the fluid are being converted through the viscosity and the friction in the fluid into thermal energy, and that's what viscous dissipation was quantifying. So viscous dissipation in fluid flow. And an example of that would be pressure drop in pipe flow. The pressure drop is a form of mechanical energy, or pressure is a form of mechanical energy. And the reason why the pressure is dropping is because that mechanical energy, there is shear, velocity shear within the pipe flow, and that velocity shear then eventually makes its way into thermal energy. Another example of increasing randomness in a system is the mixing of two fluids. So what I'm going to do now is I'm going to show you a video clip, actually two of them, of two glasses of water. And within each glass, I'm going to drop a couple of droplets of a liquid food coloring. The glass on the left is at a cold temperature, while the one on the right is at a hot temperature. So let's take a look at this process and see what goes on. So what we could see from the video clips was that the glass on the left at the lower temperature, the main form of mixing was due to diffusion alone. So that would be molecular motion within the two liquid mixture. And you'll notice as the droplets went in, they descended rather rapidly. That was due to the fact that I was dropping them from a higher point, and so they had kinetic energy, and that forced them down to the bottom. And also the food coloring was probably a little denser than the water. The example on the right-hand side with the hotter temperature fluid, what we saw there was a mix between natural convective currents in the heated fluid, the heated water, as well as we had the diffusion of the two species mixture. And so that is what was going on in those two video clips. And you notice the one with the combination of natural convection as well as the diffusion, actually the mixing took place much more rapidly than the one on the left-hand side. But once you've mixed these fluids, it would be very, very difficult to unmix them. And so entropy there would be quantifying the disorderly or the mixing of the two different fluids. So the entropy was increasing as that process went on. And a final example is a chemical reaction. Now in chemical reactions, we usually have two different chemicals that are reacting with one another. A very common one is that of combustion, where we take a fuel and we are sending it through an oxidation reaction, and that's something that we will be looking at later on in this course. So let's take another look at another video clip of a handheld lighter at the chemical reaction there. So what we have in the lighter, there's butane, and when you pull the trigger on the handheld lighter, that causes a spark at the tip of the lighter to engage, and that spark then causes the butane and the oxygen in the air to combust. And after that chemical reaction takes place, it would be very, very difficult to take the resulting thermal energy, so the flame, and then send it back to the original components, the reactants that we had in that chemical reaction. So that is another example of entropy generation and entropy increasing.